Alright, in this video I'm just going to discuss some different aspects of light. What we call light is actually just a small part of uh, what is known as the electromagnetic spectrum. More specifically, we're talking about this visible portion of the electromagnetic spectrum we usually say light. So here's just kind of a neat graphic that shows at the top the scale of what the wavelength of light is, because light is a wave. So there's a big, huge continuum of what the wavelengths are. So just some pictures to give you an idea of how big that is. So if visible light has a wavelength of around 10 to the negative 6 meters, so that's about the size of a bacteria. Gives us the name of those types of waves. So starting all the way at the longest wavelengths are radio waves, with wavelengths longer than a football field all the way down to a baseball. At that point we start calling them microwaves. And that gets down to about the size of a cell, at which point we call them infrared. Into the visible, ultraviolet, then X-rays, and then gamma rays. And then just different sources of those types of radiation. So you can see, like, we as people, we give off infrared light. Light bulbs give off a lot of infrared and then also visible, at least the regular incandescent ones. The scale below shows us the frequency. So again, as the wavelength gets bigger, on this end, the frequency is going to be smaller, still really big numbers, and then as wavelength gets smaller, frequency gets bigger. The bigger the frequency, also the higher the energy of the photons given off. Okay, so when we'll kind of can see that if blue is a required color to make something happen, say like a chemical reaction, red light can't do it because it's lower in energy. Light is a wave and it travels at a certain speed. The speed of light is equal to 3 times 10 to the 8th meters per second. Okay, so light does travel at a finite speed. This speed is called c in physics. So a lot of times we say that this equals c. So like in Einstein's famous equation, equals mc squared, the c is the speed of light. The way the speed of light is measured, if you take a light source and that light source hits a pane of glass, it will reflect off the pane of glass through this rotating strobe disc, bounce off a mirror, and come back. When you have the rotating strobe disc going at just the right speed, the light will, every time it bounces and comes back, it will make like a continuous beam to the observer. And so if you look at the time span in between each little window coming by is the same time as it takes to go to the mirror and come back. So there you have a time, you have a distance, and you can calculate the speed of light. So that's one way of calculating out the speed of light. These days the speed of light is known so well, we actually use the distance light travels in a certain amount of time to define things that's like how long a meter is. For sources of light, we can either have luminous bodies that emit their own light, or an illuminated body that is simply reflecting the light that's given off by something else. Terms for light is, we can talk about light's luminous flux, which is how fast light is emitted from a source, and we measure that in lumens. So some light bulbs will say how many lumens they are. Another way to kind of talk about a luminous flux is like how many candle power it is. Okay. And then illuminance is just how bright the light that's shining on a surface is. Okay, so the luminous flux, you can think of that, that's what comes from a light bulb, and the illuminance is how much, like, whatever the light bulb is shining on is lit up. The illuminance is related to the luminous flux by the following formula. So we can see that the further you are away from the source of light, the more your illuminance decreases, and it decreases by the distance squared. So this is inverse square law is actually really important, like in astronomy, for example. When we look at transmittance and absorption of light, objects need to be transparent, in which they let light through. Translucent where they let light through, but some scattering occurs. So, like if you look at like a milk jug, light comes through it, but it's, cloudy. You can't actually see what object's on the other side, just that there's light coming through. Or they could be opaque, in which case no light can go through. When you look at what color an object has a color based on what color of light reaches our eyes from that object. So the light can either be emitted by the object and we're seeing the color, maybe it's reflected by the object allowing us to see the color, or maybe some colors are being absorbed and then other colors are being reflected. And so that gives us our colors. When we look at light, the primary colors of light are red, green, and blue. And so those three colors make up all possible colors that our eyes can see. White is actually not a color, but a combination of all the other colors. And then when red and green overlap, you see yellow. Where red and blue overlap, you see magenta, and so on. Okay, so one thing you might be familiar with is like when you go into like your paint program and you're able to make custom colors, all the values go from 0 to 255. If you turn on all colors, red, green, and blue all the way, you get white. If you turn them all off, you get black. And by mixing these colors in different amounts, okay, you can get the different colors that we can see. So that 16 to 17 million colors you get of combinations. So I tried to show this color mixing a little bit by putting this green over the red and blue square. You can see as I dim it, the colors mix a little bit, but not real well. We'll be doing an experiment in lab where we see a much better example of how colors mix. When we're dealing with pigments in like art class or printing photographs, the primary colors are different. They're yellow, cyan, and magenta. And these are called subtractive colors because when you have yellow, you shine a white light on a yellow piece of paper and it subtracts the blue that leaves the yellow. When you have a cyan piece of paper or cyan pigment, it takes the white light that comes in on it and it subtracts the red out of it. And so it reflects back blue and blue and green add together to make cyan. When you have magenta, that's white minus green. And black is white minus all the colors equally. So when you mix up all the colors, you're subtracting everything from the white light. We can get colors for other reasons, and one of the other things we'll look at in physics class is you can get colors from interference patterns on thin films. So what happens is light comes in on a film, and some of the light will reflect off the surface of the film, and some of the light will refract into the film and then reflect back off the back side of the film, and then it will come back out again, and you will get destructive interference whenever the thickness of the film is equal to 1/4 of the wavelength. So if you have white light coming in, and let's say the thickness of this film is equal to 1/4 of the wavelength of green light, the green light will be subtracted out, and only the red and blue will come back out, and red and blue will be magenta. So here we see on this film, wherever it's magenta, the thickness is some multiple of 1/4 of the wavelength. And then you get constructive interference, and so this is, depending on what happens, is the film optically less dense than the surface, or is the surface less dense than the film. So depending on which case you have, you could also get interference where the light comes in, gets same thing happens, but now you're getting constructive interference, and so the colors are getting shown even more than they would be instead of being negated out. Light is a wave again, and you can think of light as a transverse wave, and since it is similar to a transverse wave, you can polarize the light. So normally light from normal sources, all the waves kind of vibrate back and forth in all different directions, as seen in this graphic here where the light comes off the sun. It vibrates both horizontally, vertically, and actually all directions. When it hits the surface like the surface of the water, it becomes polarized, where all the light that reflects off actually is only vibrating back and forth horizontally. So if you're using polarized sunglasses, what that does is it cancels out light that is in all the directions. And we'll look at polarized light in lab also. So that's all there is for notes. Not too much that I'm going to introduce at this point. We'll talk, get a little bit more in depth in like how some different aspects of light work in future videos.